Thank you very much for giving me this opportunity to talk in this nice institute. Okay, I would like to talk about a kind of deformation of the generalization of so-called AKSZ sigma model, and that the purpose is the generalization of AKSZ construction, so-called AKSZ construction, and that we generalize some geometric structure, and that we want to consider some possible application to the higher dimensional physics, for example, brain physics. So it's only the one page is the explanation of so-called AKSZ sigma model. AKSZ sigma model is a mathematical method to construct a kind of sigma model that based on this is a differential graded simplex structure on mapping space. Mapping space from the differential supermanifold to the so-called differential graded simplex manifold called QP manifold. And the sigma model is a sigma model on map from the two mapping space of two manifolds. The interesting thing is that the AKSZ sigma model is directly construct so-called BV and BFD formalism of some BF type topological sigma model. Usually, the BV and BFD formalism are very complicated, so difficult to make BFD action. But this method is a direct geometrical and simple method to construct BV formalism, BFV formalism, and so on. So we want to generalize this construction to more general field theories. This is the simplest. Yeah, I'm not sure it's simplest, but the example of the AKSZ sigma model is a two-dimensional case is a Poisson sigma model, so-called Poisson sigma model. Poisson sigma model is the sigma model from two dimensions manifold to target Poisson manifold. Maybe not so. I don't think we need many explanations about Poisson sigma model. With Poisson sigma model, and we have two fundamental fields that are mapped from sigma to m, and one form taking value of the Pulver code t star m, and the action functional is first term is the first differential of ADX term, and the second one is the Pulver constructed from the Pulver code Poisson, so-called Poisson bivector field. This is the action functional. So this Poisson sigma is one example of the AKSZ sigma model. The interesting, important application is that this model gives a deformation quantization formula on Poisson manifold. This is the definition of Poisson structure. That we can generalize this the Poisson sigma model by adding third term, but H, where Z is a three-dimensional manifold with boundary sigma, two-dimensional manifold. Then the H is three form. That we can add pullback of three form at third term. This is so-called Wessling term. But this model is not the AKSZ sigma model. But this model is completely consistent if we impose some geometric condition on target manifold. This condition is the so-called twisted Poisson structure. Twisted Poisson structure is given by like this, where pi is a bivector field and H is free form, closed free form. if pi and h satisfy this condition, pi s is the s. This is the Schouten bracket, so-called Schouten bracket, and pi. This is the contraction of the three pi and h.
Consistent means what?
Consistent means if target space structure has this equation, this this is consistent as a mechanics. Mechanics mean that there is a constraint in this model. In the Hamiltonian formalism, constraint is first class. In the Hamiltonian formalism, in the Lagrangian formalism, there is a gauge transformation in this model. Gauge transformation A is a one form, so there is a gauge transformation. Gauge transformation is closed. Gauge invariant. This model is gauge invariant. Yeah. So we can this model is completely consistent as a mechanics, right?
And I think the other one is also consistent. It's just maximalism metric. So it depends how we formulate it. Is it first class constraints or positropic submanifold? If and only if pi is a Poisson bivector, it is all H. That's what we did in the first paper. And then it has H visit Poisson. H constitutes the symplectic form of the loop space.
So the talk is that we consider similar deformation in the higher dimensional sigma model. This is it. So some people propose a kind of non-associative generalization of star product formula by H. So yeah, deform the star product formula. So in my talk, I'd like to generalize the two-dimensional sigma to higher dimension, and consider some geometric condition similar to twisted Poisson structure to make the theory consistent. So I explained the first action function of this model, our model. The similar directories, as a directory generalization, we consider n plus one dimensional manifold, and with boundary n dimensional manifold is sigma. And we consider some vector bundle. Later, we assume vector bundle is a real algebroid. And we consider the mapping space. We consider sigma model on this mapping space. We introduce four fields. This is a map. X is a map from Z to M. This is a scalar field. The one form field, A, and n2 minus 2 form, and Y, and n minus 1 form, Z. We can introduce more fields, 1 form, 2 form, 3 form, 4 form, but it is only the more complicated, so we only consider this field. Therefore, this is a reason, the technical reason. The more first generalization. So we consider this action functional. The first two term is a direct generalization of the BF type kinetic term. This is n minus 1 form 0 form, and n minus 2 form 1 form. This is kinetic term. We add all the possible n form terms. We have only three terms. This one, this one, this one, and the coefficients. In this case, in this level, coefficients function is arbitrary, and we consider deformation term, the integration of the pullback of n minus 1 forms. This one as a generalization of the twisted Poisson case. So this is the action function of our model. If h equals to 0, this is the example of AKSZ sigma model. So we can, but h is not 0. This is not AKSZ. So target space is a vector bundle. This is I is the index of the base manifold. A is an index of the fiber. So it's a vector bundle.
Target is T star E. I think T star shifted by something.
T star E. T star is the target. Yeah. T star E.
Which is a vector cumulative. E is a Lie algebroid, then T star is a
Target is T star E.
then a QP structure. If I understand correctly. Without it.
Yeah.
Right. So you need to have AKSZ sigma model, you need this corresponding to the degree of the symplectic form on the target and the dimension.
Yeah.
Something the dimension n, right? Symplectic form of dimension n on the target.
And the symbolic dimension is n. Yes.
T star E.
T star needs to be shifted, I think, correspondingly to the dimension.
Yeah, no. The n minus one. N minus one. The target space is n minus one. Symbolic form, graded symbolic form n minus one in the case of AKSZ. But any special case of AKSZ, it is more we can.
Since your geometrical data is just the algebroid, so you're telling me that you can produce with the algebroid symplectic symplectic manifold of degree whatever n minus one.
Usually, the algebroid is realized as degree one graded simplex. Degree one and QP manifold. Yeah, but we realism can be generalized to the any n minus one n degree n QP manifold. Yeah.
The vector feed on E, you give to the function the bundle of the shifted by degree n minus one.
Right. Yeah, with degree n minus one, we can naturally constructed. We can construct naturally the sigma model from n-dimensional manifold to the target space. Yeah, this is normal AKSZ.
I think you take the two-dimensional case, you take E, the Lie algebroid to the twisted Poisson does not correspond to this.
Twisted Poisson cannot be constructed.
But the H twisted is not.
Not AKSZ, constructed by AKSZ.
You take Poisson sigma model in this way, no? The two-dimensional case.
Yeah, Poisson sigma model is AKSZ.
The T star E of T
Yeah, right. T star M.
Would be the
Only the T star M case, not general.
in two dimensions doesn't make take the Poisson sigma model of the dual of the algebroid.
Yeah, maybe the
Yes.
negative degree.
That's a good question. Does it general, I mean, does this the normal twisted Poisson sigma model a special case for the Lie algebroid in M? Or
And
just the base?
not the special case. Not the special case. The good question. Twisted Poisson sigma model is not special case of this model.
So it's not for E equal just the base manifold with zero. It could be big, no?
No.
But you don't think good structure. Okay.
Yeah, the in two dimension is the Lie algebroid is not the general Lie algebroid E, the Lie algebroid T star M. Only this case realized, yeah. So only in two dimension, the two dimension is special. Yeah. So we need some general. We want to consider generalization to general Lie algebroid case. So we choose this action functional in higher dimension. Of course, it is this action functional is possible in 2-dimension or even in 2-dimension, but it's not twisted Poisson sigma. Different one. That some kind of the we enters 4 fields, so we generalize the twisted Poisson on T star M to vector, general vector band.
Maybe it's like this, if you take a Lie algebraic, then its Goldachern bundle is a Poisson manifold. And then you take that as a Poisson manifold.
Yeah, right, yes. Yeah, so, yeah.
It is the one of E star.
Yeah, right.
It's a special Poisson manifold.
Yeah, right.
That's a special case.
Yeah, right, you are right. So, for simplicity, I fix these two functions in here, this one and this one, as Lie algebroid. We can consider more general algebroid, like, for example, Courant algebroid and so on. But for simplicity, in our case, in this talk, we fix this is uncommable. Rho is uncommable Lie algebroid, and CABC is the structural function of Lie algebroid. We assume that this equation, the identity, Lie algebroid. I'm not sure. I should explain Lie algebroid for you, or the Lie algebroid is the vector bundle, and with some anchor map E to Tm and some Lie bracket, and this to operation must satisfy this Leibniz rule. This is a generalization of Lie algebra. So there is some many example, including Lie algebra and some tangent Lie algebra and so on. As already you said, from Poisson manifold, if we have Poisson manifold M, T star M has a Lie algebra structure. Anchor map is defined from the Poisson bivector. Poisson bivector is bivector, so we can define this map from T star M to Tm, and the Lie bracket is defined like this. So we have a Lie algebroid from two operation and Poisson tensor. If we have twisted Poisson structure, we also obtain Lie algebra structure on T star M by deforming the Lie bracket definition of Poisson structure like this by using closed free form H. So this is, we have Lie algebroid on T star M from twisted Poisson structure. So twisted Poisson, so Lie algebroid is a very natural object if we want to consider higher dimensional generalization. So we prepare some mathematical concept to explain my geometry. First one is a differential, so-called Lie algebroid differential on the space of E differential form. E differential form is the wedge product, section of wedge product of TE star. This is a generalization of the differential form. The Lie algebroid differential is defined like this, with the ED satisfies this square to zero condition. So it is differential. The increasing the EM form to EM plus 1 form. So we have two differentials. D is a normal drum differential, and ED is a real algebra differential we introduce on real algebra. So we have to some double complex, but and we can define two connection corresponding to differential. One is a normal connection. This satisfy. We denote nabla by normal connection on the vector bundle. But another connection corresponding to ED, E differential, is called E connection. E connection on the vector bundle is this is the replacement of the T star M to E star, right? And so it satisfies a kind of Leibniz rule. E connection or vector bundle E prime, another vector bundle is linear map satisfying this Leibniz rule. This is a replacement of the T star M to E star, right? If we define usual connection, we can obtain canonical E connection by this equation. This is the E prime. We consider E prime is equal to Tm case. So E connection of Tm is canonically defined like by this equation. This is, but we can. This is not the unique equation, E connection. We can. So, but yeah. Anyway, E connection exists if the normal connection exists. Okay, we from now we consider physics. We compute the normal Hamiltonian form by using the normal method of analytic mechanics. That we consider time and space direction, and first we consider canonical coordinate. Canonical coordinate is x and a, 0 form and 1 form, and we can define canonical conjugate momenta in normal formula or in the analytic mechanics. So this is this one. Essentially, a canonical conjugate of xi is n-1 form. The canonical conjugate of a is n-2 form. S is with space direction on sigma. Then there is some constraint, 3 constraint. The PA 0 it means that the time direction. This time direction is 0. So we can construct Hamiltonian by this Legendre transformation. Where B is this defined from H like this, and we can construct simplex form, and then we can define Poisson bracket from this simplex form. So from this primary constraint we obtain secondary constraint. The secondary constraint is 3. We have 3 constraints like this, where T is so-called E torsion. It's a torsion E connection. The interesting thing is the component. Completely written by by the geometric quantity. So sorry. It's okay. Thank you. And Hamiltonian is described by the constraints like this. So we require we compute the condition of this mechanics to make this mechanics consistent. Consistent means that the constraints must be the first class. First class means that the constraint Poisson bracket of constraints must be involutive, like this. And the Poisson bracket between constraint and Hamiltonian must be proportional to constraint. Two conditions must be satisfied for consistency of the mechanics with constraint. Okay, this is the condition of the first class constraint. So we compute a Poisson bracket of these constraints, and this is next to the simple comparison calculation, or only the simple comparison configuration. So we explain the solution of this computation. So the condition, we already fix the condition, the identity of the first row and C. So remaining part is J, the condition for J and H, this one and this one. So I explained the geometric condition to make the theory consistent. So first one is H. H is nothing but the multi-simplex structure. H must be closed. So if closed n parameters plus one form, it is called the n-parametric form. Pre means the omega is not necessarily degenerate and non-degenerate. If it is non-degenerate, it is n-parametric form. It's called the n-parametric form. Yeah, this one. Of course, the one-parametric form is a simplex form. So first condition is the manifold M is pre-n-parametric manifold. It's a notation. The k times contraction of rho and omega is denoted like this, or like this. The definition is like this. So we import the condition. The condition of one condition, this one. ED is already explained. ED is an irreducible differential. J is the term, the coefficient of this term in the action functional. This one. N form. This is a completely anti-symmetric tensor. So we have this differential. From this differential, we obtain n plus 1, En plus 1 form. So then this n plus 1 contraction with omega and rho gives the n plus 1 form, En plus 1 form. So this equation is meaningful. if J satisfies this equation, J is called compatible with the rearrangable structure and the pre-enucleatic structure. And this must be consistent with the d square equals 0 condition. So we have to check this condition. This condition is satisfied if this equation for rho and d omega equals 0. If we consider rearrangable, this equation is satisfied. This is the morphism. This means rho is a morphism of the E to Tm. And of course, we assumed the omega is closed. So this is okay.
What is the condition omega? Any reciprocity?
Omega, this one?
As it's not an if and only if, it's only if, it's one direction of proposition.
Proposition is not only if this equation is satisfied, this equation is satisfied.
Yeah,
This is
right? Because otherwise omega 0, you cannot get the first equation.
the usually this is some the condition is this one plus this one. This is a summation. Not necessary.
It's not necessary.
Not necessary. Not necessary.
Only sufficient.
Yeah, only sufficient. So yeah, this condition means that, for example, if we don't need rearrangable, we only need, for example, all of the rearrangable for this equation. Yeah. So there is a possibility to generate rearrangable to more general algebra. So my result is like this. If E is suppose that E is a rearrangable, and that omega is pre-enucleatic form, it means that closed form. And then 3 constraint, first class constraint, if and or if this J satisfy equation 1, this one. So our mechanics, our sigma model is the consistent if target space geometry satisfied this condition. Concretely, the Poisson bracket of constraints are like that. This is rather complicated, but anyway, we can compute by hand. And where the S is some geometric quantity on rearrangable. This is so-called basic curvature. It shows some consistency of the two curvatures, to connection, normal connection and the connection, like this. So the summary. So the solution to of like this. The first one is target base manifold is the pre-enucleatic multi-symplectic manifold, and the vector bundle is rearrangable. And J, we have another one more condition. J must be the compatible EN form. If 3 conditions are satisfied, our topological sigma model is consistent. It's a kind of direct generalization of the AKSZ sigma model. If H equals 0, this is the AKSZ. So this condition is my claim is this condition is a very good condition. There are many important geometric structure satisfy this condition. Therefore, we show some examples of this condition. One is a twisted Poisson structure. Twisted Poisson structure satisfy the condition. So the condition of twist Poisson structure can be written by as this equation. ED is the real differential on T star M, and this one is nothing but the H is omega and J is pi in our structure. So this is an example. Another example is a kind of higher dimensionalization considered by Chasista Brack. Yeah, Brack is. This is the TM case. E equal the vector bundle is Tm. In this case, the vector bundle is T star M. In this case, the J is multi-vector field R. This is R equal J. So the so-called twisted R Poisson structure is defined by this equation. This is the equation nothing but the R equals J and H equals essentially omega. This is the example. Another important example is the moment map. Moment map is the mathematical counterpart of the so-called Noether's theorem, and it is defined on the manifold with Lie group action G. The Lie group action induces the Lie algebra action as an infinitesimal differential transformation. From this Lie group, Lie algebra action, we can define Lie algebroid, so-called, it is called action Lie algebroid. So we can construct Lie algebroid from the Lie group action. So moment map is defined M to G K star. Satisfy two equation. This is the Hamiltonian equation, Hamiltonian condition. Moment map is a kind of Hamiltonian for this action law. And the second one is the so-called equivariant condition. These equations are the equivalent to these equations. Using first equation, second equation is changed to second red equation. The red equation is nothing but the momentum map, the mu 0 equals J, and the omega is the simplex form. So this is the mu 0 momentum map satisfy the previous compatible equation, this one. Right. We can generalize the momentum map to the multi-simplex structure. This is one version is a homotopy moment, so-called homotopy momentum map. Homotopy momentum map is defined as follow on multi-simplex manifold, n-plectic manifold. Omega is the non-degenerate closed n plus 1 form. And assume an action of Lie group, similar to momentum map case. They consider, it's the typo, then consider a series of the 0 form to n minus 1 form. This is 0 form to n minus 1 form, taking value of the wedge product of K star. And impose this equation for this mu. DC, where D is the drum differential, and DC is the so-called the Chevalier-Eilenberg differential on Lie algebroid. So this equation is the direct generalization of the momentum of theory, momentum of condition.
Did they write it like this, or was your recommendation?
Sorry?
Did they write it like this, or it's your recommendation?
They write this equation. Yeah, a version. Yeah, we can. There is they propose they propose various versions. For example, co-momentum version, co-momentum map. The momentum map M to G star, but
These last equations.
they also write this. Also write this equation. Yeah. So the and we consider only zero form part, mu zero, among the zero form part satisfy this equation. So this equation nothing but our equation or compatible equations. So only the zero form part. We only choose zero form part, so this zero form part is satisfied. So the homotopy momentum section, homotopy momentum map satisfy part zero form part. Zero form part of homotopy momentum map satisfies compatible equation. Okay, recently the rearrangable generalization of the moment map is proposed. This is the example. Thomas, inspired by Thomas, the paper, the Broma-Weinstein defined the generalization of moment map to the rearrangable setting, and in order to define a generalize to the moment map on rearrangable, we need to introduce connection. This is a normal connection. The idea is that it's simple. So moment map is a map from M to G star. So this is regarded as a section of the trivial bundle M plus G star. So we can consider generalization to M plus G star to general dual of rearrangable. This is so it's natural to consider the section of the dual of algebroid. It is called the momentum section if satisfied two equations. This is the direct generalization of the condition momentum map to condition this one is directly generalized to this one by introducing connection. Then we see second equation. So this is nothing but the condition for the compatible En form where n equal 1 to n equal 1 in simplex case. So this satisfies the condition, compatible condition. We can consider pre-predictive generalization of the momentum section. In order to consider generalization, we have to introduce two connection and E connection, and impose the generalization of the homotopy momentum map. It's a kind of direct generalization of homotopy momentum map to rearrangeable setting by introducing two connection. The zero form part is nothing but that the zero form part satisfies this equation. This equation is nothing but the compatible En form condition. We consider this one. So there are many important examples in our geometric conditions. And okay, finally, we analyze some Dirac structure interpretation of our geometry in order to there is a so-called Dirac structure on realgebroid, the Courant algebroid. It is a kind of the we consider substructure of the larger the algebroid. So the larger algebroid is so-called linear algebroid. In fact, it is also called the Leibniz algebroid on E plus E star n plus 1 and the wedge product of n minus 1 wedge product of E star, where the E is a real algebroid. So we obtained some structure on this space. We have three operations on this larger space. One is a symmetric bilinear form. Second one is the row hat, the anchor map on this algebroid. It is type of E star. And we can define a kind of higher Dorfman bracket on this bilinear bracket on this space. This definition is like that. U and me, this is a U and V as the section of E, and alpha and beta is the section of E, this one. So we can define three operations that the three operations satisfy some identity. So we call this algebroid Lie algebroid. So higher Dirac structure is defined like this, that the higher Dirac structure is a sub-bundle of this bundle, satisfying the two conditions. The symmetric bilinear form is called 0, and the higher Dorfman bracket must be involutive. So my result is if J is En form, En form, and we can define this one. This is the element of the section of this bundle, larger bundle. Then E is the satisfied, J is satisfied compatible equation, this one, if and or if Lj is a higher Dirac structure of this bundle. So this equation is realized as a higher Dirac structure of this larger bundle. So if we formulate like this, we can there's a possibility to generalize this structure and the sigma model. Okay, on. So we can conjecture the possibility to generalize our topological sigma model by adding some more terms, 1 form, 2 form, 3 form, 4 form, and the impose the consistency condition. My conjecture is this should be a general higher Dirac structure. Right? No. This is only the special case of Dirac structure, a higher Dirac structure of this bundle. But of course, we can consider more general higher Dirac structure by satisfying this condition. But we don't consider, we don't have the corresponding topological, the sigma model yet. But anyway, this is a good geometric structure, so there is a possibility to formulate, to formulate the corresponding topological sigma model corresponding to the general Dirac structure, like the kind of the generalization of there is the sigma model, so-called the Dirac sigma model in 2 dimensions already. So So maybe we can construct the similar generalization to in higher dimensional case. Yeah, realize higher Dirac structure. This is the possible direction of generalizations. Okay. Okay, I have finished. There is a Q manifold description in this structure, so I skipped it. So, but it is interesting. Important thing is the Q manifold. This is the Q manifold, but not QP. So QP manifold is a differential gradient manifold. So if the structure can be formulated as QP manifold, we can construct the AKSZ sigma model. But it's not QP. It is only Q manifold. Or simplex structure and Q is not compatible. So it is the important thing. So, okay. This is a summary. We consider deformation of AKSZ sigma model. It is the higher dimensional generalization of twisted Poisson sigma model. So determine the geometric condition on target space to make the theory consistent. It's the constraint is first class and gauge invariant. In this geometric structure, there are many examples, include important example. So I think it is interesting structure. This geometry is formulated in terms of differential grade geometry. It is the natural thing for the AKSZ sigma model, but it is Q manifold, but not QP. The BV formal is very complicated. We construct the BV formal by hand, order by order. In higher dimensional cases, much more fields are needed, so it's very complicated. So only in three-dimensional case, we constructed the BV formal by hand. But we need the more simpler method to construct the BV formalism. So it is the problem. There is the possibility of generalization. Also, possibility of generalization of this model. This is the first step of the generalization of the sigma model by introducing general all the forms. So the BV formalisms are very complicated, so we need some simple geometric method like AKSZ sigma model. Quantization may be interesting as a generalization of deformation quantization, and maybe we have application to some string theory and so on. It's all. Thank you very much for listening.
Have you thought about, because if you go one dimension higher, it is an AKSZ. You could include twist H as an AKSZ theory in the data in the target. For example, in the twisted Poisson case, you think of the current algorithm, twisted H, and then this is a three-dimensional theory. So I think this would be general.
I see. The geometric structure is possible. But the mechanics, it's different mechanics. It means that the equations of motion are different. Equations of motion are different. So as a mechanics, it's different. So BV formalism is different. So as physics, it's a different theory. A geometry is the same.
Uh-huh.
Yeah. So
But if you think of in 3 dimensions, like a grain or a boundary condition, wouldn't that lead you to this twisted Poisson sigma?
But that is not how it essentially tried. The point is that it doesn't seem to give the right idea. It looks everything right, but it doesn't seem to be right.
Okay.
It looks that we need to use some equation of motion at some point to really.
Yeah.
So it's just not the right idea. So people claim that, but then I looked at it and it's just not true. It's just not right. Okay. At least in my knowledge, I mean, but I remember that
Yeah.
we said that you and Miguel, we were working on something similar. So
Yeah, but it wasn't twisted.
yeah, but still.
Yeah.
Maybe it does work in the end of the day, but I don't know how. At least it's not a normal BV. That I can.
Yes.
But there are some rules in BV what it should be. That's not the case. It should be very simple, very straightforward.
Yeah, I think it's similar to some difference of Chern-Simons theory and Western double model in 2 dimension. Yeah, this is of course the symmetry based on the Lie group is the same, but and the theory is different. For example, 2-dimensional theory is more the good candidate for example, for the string theory and so on to analyze string theory. So it's like that. So lower dimensional case is more easy to analyze. So we consider lower dimension theory. Yeah. Of course, the BV formalism is quite different. BV action is quite different. So yeah, we want to try to understand such a difference. Yeah. It's also our motivation that the n+1 dimensional theory and n dimensional theory. Yeah. This such a correspondence state of 2 theories is one motivation and so on. Yeah.
In the case of the twisted Poisson sigma model, okay, your solution, you take h equals 0.
Yeah.
Reduce to the Poisson sigma model for pi or to the Poisson sigma model for the dual algebra.
Yeah.
Understand, no? You have the Poisson sigma model for pi, but it's a second Poisson structure, which is the one in the dual vector band of Tn.
Yeah.
What is the Poisson sigma model that you get when h is 0? The Poisson sigma model for pi, or is the Poisson sigma model for the dual algebra?
Also, see model pi.
And the algebroid on the dual has a Poisson structure, right? So I can take a Poisson sigma model with that target. So my question is, when you take your solution, your PV solution for the twisted Poisson sigma model, is it and take h equals 0? So is this the ordinary solution for Poisson sigma model with target pi, or with target the dual algebra?
Yeah. Sorry, my question. Your question is the if h equals 0, the BV action is reduced to.
Yeah, what is the model if h equals 0?
H. So okay.
So if h is 0, the twisted Poisson sigma model get like a Poisson sigma model.
Yeah.
In the thing we considered, for example, we constructed together the BV for h twisted Poisson sigma model.
BV is reduced.
If you put h to 0, you get the usual AKSZ one. But then today we discussed another type of theory, and if there you want to mention 2, if I understand it correctly, it's T star of E, which is the same as T star of E star. And E star is a cosomanifold. So there you will get the twisted Poisson sigma model or Poisson sigma model for E star. Yes. That makes the model. So
Yeah, T star is algebra. So this star is a Poisson. Yeah, yes. It means E is Poisson. E star. E star is Poisson. Yes, yes, yes. So yeah. So in this method, yeah, we realize the general algebra like this. So if H equals 0, BB formalism is reduced to the normal, the AKS action, AKS sigma model. It's okay.
More questions?
Thank you very much.